Good afternoon, guys. Welcome to class remote here. I hope you're having a good end of your week. So, we're going to jump into what we're going to talk about today here, which is to wrap up what the derivatives tell us about the shape of a graph, and then to look at another application of derivatives of a function when that function is position. We'll see that the derivatives are velocity and acceleration. So we'll study that in just a moment. So first, though, let's finish up what the derivative or derivatives of a function tell us about the shape of the graph. That really has been the theme for what we've been doing for a while now. We're looking at the first derivative being positive or negative. That tells us that the function itself is increasing or decreasing. And then last class we got into studying the second derivative and what that tells us about the function. We were able to make some connections to local extrema and so forth. So let's take that a little bit further here today, look at a couple examples and wrap that up. So I want to look at the second derivative test. We talked about this in class on Tuesday, but just remind yourself of what it says. It only is used at critical numbers. Okay, so this is a theorem that has to do with critical numbers. So we have a function with critical number at c, that's an input c, and there are two statements. First statement says if you're at a critical number and the second derivative is positive, then you have a local minimum at c. The other statement is if you're at a critical number and the second derivative is negative, then you have a local maximum at x equals c. Okay, and so let me go ahead here and jump into an example of this test, okay, and showing how this test can be used. So I've got an example down below. I'm going to pull this up so we can see it a little more closely. The example says to find and classify the critical points of the function f of x equals x cubed minus 3x. Okay, so I've gone ahead and graphed this function, and it looks like this. Okay, nice. It's actually an odd function, symmetric about the origin. So it was a nice looking graph here. Third degree polynomial. We know what the end behavior is and all of that. But we're interested now in classifying the critical points. Okay, so that's what the second derivative test allows us to do. Now, last class we used the first derivative test to classify critical points. Same goal. We just have two different tests that allow us to do this. Okay, so going to do this. So step one, here's my solution. First step is going to be to find the critical points. Okay, so to find critical points, we set f prime of x equal to 0 and solve for x. Okay, so I'm going to solve the equation f prime of x equals 0 for x. Okay, well, let's take the derivative of this function. F prime is 3x squared minus 3. And I'm going to set that equal to 0 so that I get this condition and can solve it. When I do this, I get the x values plus or minus 1. Okay, so those are the critical numbers. All right, so that's great. So I've got the critical numbers. There are two of them. Those are the only ones because notice the way I know these are the only critical numbers is because the derivative exists everywhere. Okay, so the function f is a polynomial, so it's differentiable everywhere. So I don't need to worry about that special case in the definition of critical number where the derivative does not exist. Okay, that is not going to happen for a polynomial function. Okay, so these are the only two critical numbers of this function. Now, looking at the graph, it's already apparent what kinds of critical numbers these are. One gives a local maximum, one of them gives a local minimum. Okay, but let's verify this. Suppose we weren't looking at the graph and wanted to verify this analytically using the theorem, which we're calling the second derivative test here. Okay. So how would that look? Well, my sort of next step here, so let's call this maybe step 1, and now maybe step 2 is the classify part. So let's take the critical numbers one at a time. Okay. Okay. Take the critical numbers one at a time and classify them. So I'm going to classify, first of all, let's take x equals 1. Okay. So x equals 1 needs to be plugged into the second derivative. So I know this is a critical number. I now want to find the number f double prime of 1, second derivative evaluated at that critical number, and see if it's positive or negative. Okay. So I'm going to find the second derivative, which is 6x. Okay. Thus, f double prime evaluated at 1 is 6, but to the point this is a positive number. Okay, so by the second derivative test, it follows that x equals 1 gives, let's go up and see, if the second derivative is positive, we're in case 1, that gives us a local minimum. Okay, gives a local minimum. Okay, good. And now let's classify the other one. Okay, actually, you can go ahead and do that. Pause the video now and see what you get. Classify -1, and then we'll come back in a minute. Okay, guys, so you found, I'm sure, that the second derivative test tells us that x equals -1 gives a local maximum, and we can verify that by looking at the graph, okay, and seeing here at -1, we get this local maximum value, and at +1, as we also found, get this local minimum value. Okay, we can find what those values are just by plugging into the function. Okay, very good. Now, I want to just reiterate something that we said in class on Tuesday, which is roughly speaking why the second derivative test is true. Okay, so let's just remind ourselves why this is true. Okay, and you should be able to give some kind of explanation for why the second derivative test is correct. Okay, and so here is a rough idea, and the idea is based on what concavity means. Okay, so let's just remind ourselves, to be concave up can be thought of in a couple of different ways. Okay, so concave up corresponds to, one way of thinking of it is that the graph locally lies above its tangent line. Okay, so graph nearby, at least, okay, lies above, and that's where the emphasis is, lies above its tangent lines. Okay, so that's one way of thinking of concave up. Analytically, actually this can be made into an analytical statement too, but analytically, the second derivative is positive. Okay? Second derivative is positive. Okay, we'll draw a picture in a minute to kind of explore these things. Okay, the second derivative being positive tells us that the first derivative is increasing. Okay, now both of these things are taking place on some interval, right? So this would be on some interval, a to b. Okay, we're talking about concave up on an interval from a to b. Okay, f prime then would be increasing on the interval from a to b. Okay, so all of this is localized, but if we're on a region of the domain where the graph is concave up, then all of these things are telling us the same thing. Okay, now let's think in a little more detail, and I don't think we said this in class on Tuesday. If f prime is increasing, remember what f prime tells us about the shape. This tells us that the slopes are increasing. Slopes, let's be precise, of tangent lines to the graph as you go from left to right are increasing, and that's just a consequence of the fact that the derivatives are the slopes of the tangent lines, okay? So they are increasing on the interval from A to B. Now, one way to capture this that's particularly useful is to say if the slopes are increasing, that says that the tangent lines are rotating as you go from left to right. They are rotating in the counterclockwise direction, okay? So let me say that, and then we'll try to illustrate this in GeoGebra. So the tangent lines are rotating, turning, okay, counterclockwise. Okay, so let's see if we can make sense of that. We'll go over now to GeoGebra. Okay, so here is GeoGebra, and we're looking at the same graph we saw a moment ago. I'm going to take a point on this graph in a region of the domain where the graph is concave up. Okay, so here's a point on the graph. At that point, the graph is concave up. We'll verify that in a moment. Okay, but I'm going to now draw the tangent line at that point. Okay, and notice what happens as I move this point to the right. Okay, notice the tangent lines are changing, but they are changing by rotation in the counterclockwise direction. Okay, so on this whole region, okay, the graph is concave up. So as I move from left to right, the tangent lines are rotating in the positive, or in the counterclockwise direction. Okay, and conversely, so if I turn all of these statements around, okay, if the graph is concave down, the graph lies below its tangent line. The second derivative is negative. This first derivative is decreasing. The slopes are decreasing and the tangent lines are rotating clockwise. Okay, so if I bounce over to GeoGebra again on the negative portion of the domain, okay, where the inputs are negative, as I move from left to right, notice the graph lies below its tangent line. The second derivative is negative here. Okay, we'll see that in a minute. The slopes are decreasing, and that has the effect of rotating the tangent line in the clockwise direction. As I go from left to right, those tangent lines rotate clockwise. Okay, whenever I hit this point, they turn around and start going counterclockwise because the graph is switched to concave up. So to understand why the second derivative test is true, to kind of come back and zero in on this information, the second derivative being positive corresponds to the graph of the function being concave up. And if you have a critical number, right, so let's think about what the second derivative test tells us. We have x equals c is critical number. Okay, that means the derivative is equal to 0 at c. Okay, and additionally, in case 1 of the second derivative test, we have the second derivative is positive. Okay, so if it's positive, that says the graph is concave up. Okay, as we've just seen, so the graph is concave up. If the graph is concave up and the derivative is 0, okay, we're in exactly this scenario. So say here is, I think we drew a picture like this in class Tuesday. If this is x equals c, the graph passes through this point. The tangent line there is horizontal because the derivative is 0. Okay, but the graph is concave up because of the second derivative being positive. that forces then this sort of picture to be going on. Okay, and so we have a local minimum at C. All right, and on the other hand, in case 2, we're still at a critical number, so derivative is still 0, but we have the second derivative being negative. Well, that corresponds to the graph being concave down. And in that case, the picture, the analogous picture, is this guy at critical number C. Graph passes through this point. Horizontal tangent line is here, okay? But the graph is concave down, which says the picture is something like this, okay? All right, guys. So we have a local maximum in that case, all right? So the second derivative test is best understood in terms of interpreting the second derivative in terms of concavity, okay? So concave up or concave down. All right, so that brings us to sort of one last notion that's related here before we can do a nice big example in all its glory, and that's the idea of an inflection point. So an inflection point is simply a point on the graph where the function changes its concavity. So it goes from either changes from concave up to concave down or from concave down to concave up. Another way to say that is that f has an inflection point when the second derivative changes from positive to negative. Remember, that would be concave up to concave down, or from negative to positive, that would be concave down to concave up. Okay, so if it changes concavity, then you have an inflection point. Okay, all right, so let's work an example. Our example will be example 2 here at the bottom of this, well, toward the middle, at the middle of the screen at this point, to sketch the graph of this polynomial, this fourth degree polynomial. Before we get to this though, pause the video and try what you see in the box above. Try to find the intervals of concavity and the inflection points for this function that we were working with earlier, okay? X cubed minus 3x. So find the intervals where the graph of that function is concave up and concave down, and then find any inflection points that the graph may have. Okay, so try that now. Okay, so together we'll do example 2, all right, which is a kind of complete example that's going to take us through sort of a summary of the things we've done as we study the shape of a graph as it's determined by the derivatives of a function. Okay, so the example says to sketch the graph of the polynomial, this fourth degree polynomial using calculus. Okay, so when I say using calculus here, and without just graphing it on a calculator or GeoGebra, I mean catalog the data that can be learned from an analysis of this function, looking at its intercepts and its intervals of increase and decrease, and its inflection points and concavity and etc. And catalog all of that information, and then use it, if you can, to draw a reasonably accurate graph of the function. Okay, this will bring together a lot of the things that we've done in the last lecture or two. Okay, all right, guys. So I'm going to start by giving you a hint. Okay, so this is a fourth degree polynomial. It's not always easy to find the x-intercepts of a fourth degree polynomial. So I'm going to give you a hint. The hint is that 4, 0 is an x-intercept. Okay. I want to see why that's actually a really good hint that's going to get us going in terms of analyzing this function. Okay, so step 1, I'm going to do this in multiple steps. First thing we're going to do is find the intercepts, x and y intercepts, okay, of the graph of this function. So let's find the intercepts. All right, so I'll start with the y-intercept. That's the easy one. Okay, to find the y-intercept, we set y equals 0. Excuse me, set x equals 0 and solve for y. Okay, so this is y equals that stuff. Y is the output, and so we set x equals 0. So we get f of 0 equals, well, 0, okay? So that tells us that the y-intercept is the origin, 0, 0, okay? So that's good. A function has only one y-intercept, okay? All right, and then the x-intercepts now are to be found. Okay, so we're going to set now y equals 0 and solve for x. So we get the equation 0 equals f of x, which is all of that stuff. Now the first thing I notice is I can factor out an x from all four terms. Okay, so that leaves x cubed minus 12x squared plus 48x minus 64. Okay, now knowing that, going to the hint now, so it's like my job to continue to factor this thing to find all of the solutions of that equation. Okay, of course I set this equal to 0. To factor this thing, if possible, could be difficult, right? So even though we've reduced it to a third degree polynomial, it's still not obvious, you know, what that factorization might be. Now, with the hint that 4, 0 is an x-intercept, we learn that. So let's think about this hint strategically. If 4, 0 is an intercept, that means that f of 4 is equal to 0, okay? So 4 is a 0 of the function, and we know from college algebra that if this is true, then of a polynomial function, then x minus 4 is a factor of the function, okay? So that's nice. So actually that tells us we can take this function, or this third degree polynomial factor, and factor out a 4 from it, okay? So let's go ahead and do that. I'm going to do that out to the side a bit. With polynomial long division, just for the practice of it, okay? So I'm going to divide x minus 4 into that third degree polynomial, okay? Go ahead and pause the video and see what you get there. Pause the video, do that division, and we'll come back together in a minute. You should have gotten this. So dividing gave x squared minus 8x plus 16, okay? You should be able to do this polynomial long division on an exam or quiz, okay? And so that reduces our polynomial or factors our function into x times x minus 4 times x squared minus 8x plus 16. Now, that final quadratic factor also factors into x minus 4 quantity squared, okay? So we get this factorization, which I'll write more compactly as x times x minus 4 to the third power, okay? All right, so from this we see now that there are two x-intercepts, and I'll just go ahead and write them down by reading off the data from this equation. So one of them is 0, 0, okay? And we actually already knew that because if 0, 0 is a y-intercept, it's also an x-intercept, okay? Noticing that looks like a kind of scary Halloween face there. That's kind of interesting. Anyway, so 0, 0 is one of the x-intercepts, and the other is 4, 0. Okay, and there are no others. Okay, so it's like, yeah, we were given 4, 0 as an x-intercept. We found that 0, 0 is a y-intercept, which, well, it's also an x-intercept. So we didn't really gain anything from all this work, but that's not true. We did gain something, which is that we know these are the only two x-intercepts. Okay, so these are the only x-intercepts. Okay, good. So we've got some of that data nailed down. Let's move on to step 2. Okay, so step 2 is going to be to find the intervals of increase and decrease, and for that we need the first derivative. Okay, so now that we've factored the function, I'm going to use that factored form, okay, to differentiate. All right, so I'm going to use the product rule. Okay, so the product rule will make this differentiation maybe a little faster, okay? Maybe not, but I'm going to use it anyway just for practice. So recall that the derivative of two functions multiplied together is the first function times the derivative of the second plus the derivative of the first function times the second. Okay, so fg prime plus f prime g. So this is the product rule, okay, which you should know. You need this on the homework. Okay, so call that back to memory. All right, so I'm going to use just x for my first function, and then the complement, everything else, x minus 4 cubed for the second function. So I'll take the first function, x, times derivative of the second. There I need the chain rule because we have x minus 4 cubed. So we have blah cubed. This becomes 3 times blah squared times the derivative of the inside, which is just 1, okay, by the chain rule. So that's first times derivative of the second, plus the second function is x minus 4 cubed, let's write that down, times the derivative of the first function, which is just 1. Okay. Now I'll simplify this to get by factoring out an x minus 4 squared, what remains is a 3x plus x minus 4. Okay, so I just factored out an x minus 4 squared from both terms. Okay, and then simplifying that, we find x minus 4 squared times 4x minus 4. Okay, I can factor a 4 out of this last factor, and that gives me 4 times x minus 1 remains there, and then times the two factors of x minus 4. Okay, so this is the derivative function. Okay, and again, you could have differentiated the original expression for the function and then factored it if you wanted to, but this actually works a little better. Now, the zeros, or the critical numbers, are now evident. Okay, it is evident that x equals 1 and x equals 4 are the critical numbers of the function f. Okay, these are the critical numbers. Okay, why is that? Well, to find the critical numbers, we would set this derivative function equal to 0 and then solve for x. Well, we get x equals 1 and x equals 4. Okay, so that's good. Now, let's go ahead and study the intervals of increase and decrease. Okay, so for that, I'm going to draw a number line and place the critical numbers on it. So I have 1 and 4. If I choose an x value that is less than 1, I have 4 is always positive, so it's irrelevant. I'm looking here at the sign of f prime. Okay, x minus 1 is negative, x minus 4 is negative, but x minus 4 squared is positive. So I have well, 4 is always positive, times a negative times a positive when I square it. Okay, all right, so this would be, by the way, x minus 4 squared is always positive. So x minus 1 is determining the whole gig. So over here we are negative, if we're less than 1. If we are between 1 and 4, say for example 2, I plug in 2, I get a positive result, positive sign of f prime, and then over here likewise we get negative. Okay, so what this tells me, kind of marching along and cataloging information here, is that on this region f is decreasing, not f prime, but f, the original function, is decreasing. On this interval, f is increasing, and on this interval, f is decreasing. Okay. All right. So let's make that a little more formal. Okay. So therefore, f is increasing on the interval 1 to 4 and decreasing on negative infinity comma 1 and on 4 comma infinity. Okay. All right. So that's good, guys. So what can we say next? Now let's study the second derivative. Okay, so we have some information. Let's put this in a box. We know where it's decreasing. Make sure we're sort of summarizing things as we go. We know what the x-intercepts are. We know what the y-intercept is. Okay, all right, good. So third, let's go on to looking at concavity. So concavity. Concavity information is extracted from the second derivative. Okay, so let's differentiate this guy, the first derivative. So the first derivative, recall, is 4 times x minus 1 times x minus 4 quantity squared. So therefore, the second derivative, I'll use the product rule again. I'll take 4 times x minus 1 as the first function and x minus 4 squared as the second function. Okay, so first function is 4 times x minus 1 times derivative of the second is 2 blah to the first times the derivative of blah is 1 plus the second function x minus 4 squared times derivative of the first function, which is just 4. All right, so simplifying a bit, we get what? Let's factor out a 4. Let's factor out an x minus 4 from both terms. And that leaves x minus 1 from the first term and x minus 4 from the second term. Okay, simplifying a little bit, this becomes 4 times x minus 4 times 2x minus 5. Okay. I'm noticing here, guys, I left off this copy of 2 right here. Okay, that was, so I did not, I dropped that factor of 2, just slipped my eyes there. Okay, so there's a factor of 2 here, which makes this 2x minus 2 plus x is 3x, and then there is a minus 4 here as well. So we have negative 2 minus 4 is minus 6 overall. Okay, so that cleans things up a little. And now we can factor out a 3 from that last factor and get 12 overall times x minus 4 times x minus 2. Okay, double check me on that. All right, so here is the second derivative, right? So the second, and it's in nice factored form. Well, let's study its sign. So this is the second derivative. So well, not critical numbers. Okay, these would be, I guess, critical numbers of the first derivative, but I don't want to throw that out. I don't want to confuse things. Critical numbers for us are in reference to the original function. Okay, what we're talking about now are the zeros of the second derivative. Those are x equals 2 and x equals 4. Okay, and if you check, so this is a quadratic function. If you were to multiply this all out, over here the function, the second derivative function, is positive. Between here it's negative, and then up to the right it's again positive. Okay, so this tells us then immediately about the concavity. So here the graph is concave up, and here the graph is concave down. Okay, all right, so let's catalog that information. The graph is concave up on 2 intervals, negative infinity to 2 and 4 to infinity. Okay, and the graph is concave down on the interval from 2 to 4. Okay, all right, so let's put a box around that and keep track of it. Okay, that's going to inform us as to how to draw the graph of this function. All right, guys, I want to throw some additional information out here, just kind of bringing in some of the pre-calculus that we did, the algebra that we did earlier in the course, Okay, I'm going to put this all under 4, so I'm going to call this pre-calc. Okay, first of all, I guess the x and y intercepts are pre-calculus, and we've already talked about those. But let's talk about asymptotes. Okay, are there any vertical or horizontal asymptotes? When you're graphing a function, that's a useful thing to know. This function is a polynomial. Okay, so it has no vertical asymptotes. You only get vertical asymptotes at when you're like dividing by 0. Okay, so that never happens in a polynomial. Horizontal asymptotes cannot occur either. So polynomials of degree greater than or equal to 1 have end behavior, which is one of these 4 types. It's either I'm just kind of cataloging. I think you guys will know what I mean. It's either this, 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 or this. Okay. And in the case of our function, we have a 4th degree polynomial with positive leading coefficient. Okay. So the leading coefficient is positive 1 plus 1. Okay. So that tells us 4th degree polynomial with positive leading coefficient has this sort of end behavior. Okay. So as you go more specifically, the limit of our function as x goes to negative infinity is equal to infinity, and the limit of our function as x goes to positive infinity is positive infinity as well. Okay, so at the large negative and large positive inputs, the outputs are large positive. Okay, all right, guys. So that's the end behavior. Okay, so this is end behavior. There are no asymptotes. Let's catalog that. No asymptotes to worry about. Okay. The domain of the function is something else we can say. Domain is all real numbers. Okay. And yeah, that's pretty complete. The only thing I skipped was the points of inflection. Okay, so let's scroll back up here just a bit, and the points of inflection are kind of made obvious by this chart that we've made. Okay, so at x equals -2, let's go ahead and insert a little bit of space here. Okay, kind of occurred to me to talk about inflection points, but then I did not. Okay, so notice looking at the graph at the sign of the second derivative, there are inflection points. Remember, an inflection point is a point on the graph where a concavity changes. There are inflection points at x equals 2 and x equals 4. Now, we defined an inflection point as a point on the graph. So this is the input where these guys occur. Okay, they occur at x equals 2 and x equals 4. But specifically, the points on the graph where the inflection points occur are 2, f of 2, and 4, f of 4. These are inflection points. Okay, so I guess I'll go ahead and just tell you what these are. Okay, you can double check that I plugged into the function correctly. Okay, so the points of inflection I found are 2, -16. Double check me on that. And then 4, 0 actually turns out to be, well, we already know that f of 4 is 0 because we know 4, 0 is on the graph. So yeah, these are the two inflection points. Double check me on that, okay, by plugging into the function the x coordinates or the x values that we found. Okay, very good, guys. So with all of this information, in view. Let's try to draw the function. Okay, so I'm going to take a clean slate and I'm going to draw this guy as reasonably accurately as I can. Okay. Now, I know, let's think about a scale here, right? So x equals 4 is an x-intercept, okay? And I know that after x equals 4, the graph is increasing always, right? So it's just going to increase and the end behavior will be going up and to the right. So I'm going to put 4 on here pretty far out on the axis. So it's 1, 2, 3, 4. Okay, maybe I don't need to go quite so far. Okay, so here is 5. There's an intercept at 4, 0. Okay, and there is an x-intercept at 0, 0. So we can anchor those 2 points on the graph. Now, we found that 1, 0, or rather x equals 1 is a critical number. Okay, so x equals 1 is a critical number. And then our other critical number was x equals 4. Okay, and we use that to find increasing and decreasing intervals. Okay, so we said the function is decreasing from negative infinity to negative 1, and then increasing from increasing from 1 to 4, and then also from 4 to infinity. And I'm noticing now, guys, that I made a mistake. So this, I think I set up above. Let's scroll back up here. Yes, right here. Okay, so when we were studying the sign of the derivative, I said f turns negative over here. This is not correct. Okay, so you guys probably caught this when I was talking. This is not correct. So the sign of this thing, the sign of the derivative, okay, looking right here at the derivative, f prime of x, okay, is negative when x is less than negative 1. It is positive between 1 and 4, but it remains positive thereafter. Okay, so let me put this in red. To indicate the change here that I'm making. Okay, this is negative. F is not decreasing, it is increasing. Oh, what did I do? Sorry, I made it negative again. F is positive here. Okay, positive, 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 remains positive. Okay, so F is decreasing on negative infinity up to 1. Okay, but not here. Okay, on that interval, F is increasing. To infinity. All right. Okay, good. Sorry about that, guys. I think I was just expecting that sign to change, but it does not because of this square right here. Okay, very good. Okay, so the function is decreasing from negative infinity to positive 1. Okay, here is positive 1, and it is increasing thereafter. Okay, from 1 to 4, and from 4 to infinity. Okay, so at x equals 1, we must have a local minimum, right? By the first derivative test, okay? So by the first derivative test, if we're decreasing to the left of that critical number, okay, so these are our critical numbers. If we're decreasing to the left of negative 1 and then increasing after it by the first derivative test, which we didn't talk about today, but we did talk about in class last time, we have a local minimum. Now, f of 1 is equal to negative 27. Okay, you can check that. All right, so negative 27 is a local minimum. I'm going to come down here to negative 30 on the on the y-axis, because that seems about like what I'm going to need. -20, -10, so forth. Okay, so -27 is approximately there on the y-axis, and then so this is the point 1 comma -27. Okay, and that's a local minimum for this function. So the graph goes through 0, 0, it's decreasing all the way, and it comes down here to 1, -27, and has a local minimum. Okay, good. Now, at 2 comma -16, we found an inflection point. So let's get that in view here. So there's an inflection point. The graph is concave up before that. Okay, so it swoops down and comes up here, but then changes concavity. It becomes concave down for a little while, and then switches back to concave up after x equals 4. Okay, so let's see if we can draw that much of the graph, right? So we've got concave down. On this part of the graph, okay, and behavior is going up, still concave down here. Okay, passing through the point 2 comma -16, and that is an inflection point, which means we change here from concave down now to concave up. Okay, so I continue, but now I am concave up over to x equals 4. Now at 4, I have another critical number, which tells me the derivative at 4 is equal to 0, which tells me that the tangent line there is horizontal. Okay, so I have a horizontal tangent line, but notice that the graph continues to increase, right? So the increase interval is from 1 to 4, but then we are also increasing from 4 to infinity, right? So this continues to increase. So it levels out and then continues to increase. It's actually behaving just like the function y equals x cubed in this vicinity, okay, around x equals 4. Y equals x cubed, do you remember, comes up. We looked at this in class, flattens out, but then continues to increase. So there is no local max nor local min. Okay. All right, guys. Cool. So, so what do we have? We have decreasing from -infinity to 1, increasing from 1 to 4, increasing again from 4 to infinity. Okay. There is a change of concavity here at 2, -16, and also here at 4, comma 0. That says we have inflection points. So this is an inflection point, and this is an inflection point. Okay. Here we are decreasing, here we are increasing, here we are increasing. We're concave up from -infinity over to +2. We're then concave down from 2 to 4, and then we're concave up again from 4 to infinity. Okay, so this is a reasonably accurate graph. Let's bounce over to GeoGebra and see how well we did. Okay. I'll draw this graph, and then we'll adjust our axes. Okay, yeah, we're already starting to see good. Some of that stuff coming through. Okay, compress the y-axis here. Okay, yeah, so there it is. Yeah, 1 comma, what did we say that is? -27 is the local minimum there. Okay, there's an inflection point at 2, -16. That looks just about right. Another inflection point at 4, 0. 0 is also a critical number, although it's neither a local max nor a local min there. Okay, and yeah, our end behavior is showing. Domain is all real numbers. Intercepts are correct. Okay, so we've got the critical information, the important information, you might say, of this graph sort of cataloged. Okay, so copy this, bring it over to our notes for comparison. And yeah, reasonably good. Okay, reasonably good. So again, the theme here, guys, and the point is the shape of a graph as it's determined by the derivatives of the function. Okay, the derivatives tell us about increase, decrease, concavity, changes in concavity, etc., in a very precise way that really gives us control, gives us a way to analyze the graph of the function. Okay, all right, so let's switch gears. Okay, guys, so now would be a good time to finish, if you haven't already, homework problems 8 through 12. Okay, so on homework 7, these problems are tailored exactly to the sort of thing we've been doing, studying shape of the graph and behavior of the function as it depends on the derivatives. Okay, so try those problems. And once you've done that, come back and let's look at one more idea today before we wrap up. Okay, so the idea is of connecting the derivative to motion, okay, and what derivatives tell us about motion. So imagine S of t is the sine distance of an object that's moving in a straight line to some fixed point. So S of t is a distance, okay? And then we're asking the question, what do the derivatives of S represent? All right. So here is maybe one way to think about this motion. Okay, so imagine you have, so I'm moving in a straight line, maybe this is the x-axis, and here is the fixed point, I'll call it 0 on the x-axis, okay? And then we have an object here, maybe it's a bug, okay, or something. It's my little bug, okay? It's a happy bug. Get some antenna there, okay? So here's a bug, and his position at time t is wherever it is, but now we're measuring the signed distance, S of t, from the fixed point, okay? So we have a bug here. In this picture, S of t would be positive. If the bug were over on this side of 0, so this is what I mean by signed distance. If the bug were over here, okay, S of t would be negative on that side, okay? So S of t tracks the distance of the bug from the fixed point at all times, okay? So we're asking now, what do the derivatives represent? That is, we want to interpret the derivatives of such a function. Okay, so S of t is what's oftentimes called a position function, okay, because it gives the position of this object at time t, okay? All right. So to think about this question, I'm going to look at two examples with you. So the first is this guy. So if a billiard ball is dropped, so now our straight line of motion is going to be vertical, okay? So a billiard ball is dropped from, let's say this is a building, okay? And so it's dropped from a height of 100 feet, right? And we have a formula for its distance from the top of the building, okay? So the ball is initially dropped here, time t equals 0, it's dropped, okay? And its height is given by, oh, this is supposed to be a negative 16, excuse me. 0 instead of a negative. Negative 16, t squared plus 100. So at t equals 0, it's at 100 feet in the air. And then as t increases, that quadratic term becomes more and more negative and brings the ball down. Okay, so eventually the ball will hit the ground, which is down here, okay, and will stop. But until that happens, S of t is a model of the position, okay, of the distance the ball has traveled downward, okay? All right, so this is the height of the ball, okay? So the question we want to study then is, what is the instantaneous velocity of the ball? How fast is the ball moving exactly 1 second after it has dropped, okay? How fast is the ball moving exactly 1 second after it's dropped? And that's a difficult question to answer because let's think about why. Distance and rate and time are related by this equation, okay? Distance equals rate times time. And the question we're asking here has to do with primarily with the variable r, okay? So we want to know what is the rate, the velocity, the rate of change of the height, okay? So we could, of course, solve that for r. So we get this equation, okay? Fine. But now to calculate a rate, it's not enough to know just one instant in time, right? We need to know where the ball is at two locations, or at two instances of time, and then we can approximate the instantaneous velocity. We can compute the average velocity easily, okay? But it's not possible to use to determine the rate just by knowing where the ball is after 1 second. I mean, after 1 second, the ball's height is s of 1 equals negative 16 plus 100, or 84 feet high. Okay, so it's come down a ways after a second. But that doesn't tell us how fast it's moving at that instant. Okay, so it's maybe a little bit helpful to view this equation, r equals d over t, as a, I want to say differential equation, but that's not the right term, as a term that's giving us changes, right? So the rate is the change in distance, right? Or the distance traveled over some interval of time. Okay, so this is not necessary, but maybe it's helpful to think about these as changes in the distance, right? How far did the ball travel divided by how long did it take to cover that distance? Okay, so what distance did it cover divided by how long did it take for that to happen? Okay, we don't have a distance traveled if we're talking about just a single instant in time. Okay, so the approach that we can take though, to figure this out is to take a couple of snapshots of the ball as it's falling, okay? So what we're going to do is study the ball as it travels. So this is a t interval. Let's see, where is it after 1 second versus where is it after, let's say, 2 seconds, okay? So let's study the average velocity. Okay? So let's study the average velocity on the interval 1 to 2, okay? That we can do, right? So this gives us a delta t of 1 second, okay? 2 minus 1, okay? Or 1 second. What about the delta d? Well, the change in the distance here would be s of 2, that's how far it's fallen after, excuse me, that's its height after 2 seconds, minus its height after 1 second. So this would be, if we plug into the formula, we get negative 16 times 2 squared plus 100 minus s of 1, which we already found, is 84, okay? So this simplifies to 64, negative 64 plus 100, which is 36, okay? 36 minus 84, pull out your calculator, is negative 48. Okay? So negative 48 feet. So in this interval of time, the ball fell 48 feet. Okay, its height went down by 48 feet. So the negative is indicating that fact. Okay, and the interval of time that elapsed is 1 second. So therefore, the rate, the average velocity, let's write AV, okay, is negative 48 divided by 1. Okay. Now, if we wanted to expand this a little bit, we could include this is like a delta D, right, over delta T. And that was what, S of 2 minus S of 1. My work is running together here, divided by 2 minus 1. And we calculated that to be negative 48 This is equal to negative 48. The units now are feet per second, right? Because we've divided 48 feet by 1 second, okay? So that's an approximation of the instantaneous velocity by looking at the average velocity. But now let's do the same thing on the interval from 1 to 1.1, okay? That is, let's take a smaller interval of time and see what happens, okay? I'm also going to, so I'm going to do a couple of calculations here, and you guys can do these on your own. Pause the video. We go from 1 to 1.1, from 1 to 1.01, and then maybe even from 1 to 1.001, and see what those average velocities turn out to be. Okay, so go ahead and pause. Maybe I'll do one more with you, and then you can pause and do the last two on your own. So the average velocity here is s of 1.1 minus s of 1. That's the change in distance divided by the change in time. Well, only 1/10 of a second has elapsed here. Okay, so you can do that calculation and then finish the remaining ones, and we'll come back together. So go ahead and pause. After running some numbers, doing these calculations, you get this these numbers for the average velocities. Okay, average rates of change of position. So I get negative 33.6, and then negative 32.16, and then negative 32.016. And what this starts to suggest is a pattern. Now, again, the idea is we're taking smaller and smaller intervals of time and seeing how the ball's position changes, okay? And then using that to compute the average velocity, okay? Now, what you should think in your mind is that this is very similar to something we've done already, okay? So this is similar to the notion of taking f of x minus f of a and dividing by x minus a. Okay, so this numerator is a change in the output. Okay, so this is delta f, let's say. Okay, and here we have the change in the input, delta x. Okay, and so this is the same sort of thing we're doing. It's just that now the function f is the position function. Okay, and once we had that, so this gave us an average rate of change of the function. Once we had that, we took the limit of that as x approaches a. In other words, as we get closer and closer to that home base location, a comma f of a, okay? And taking the limit of that gave us something that we defined to be the derivative. Okay, so this would be f prime, the derivative at x equals a, okay? So this was our definition. And so what we see is that we're doing exactly the same thing right here, right? So s prime of t would be the limit, excuse me, let me do s prime at 1, okay, is the limit as t approaches 1 of s of t minus s of 1 over t minus 1, okay? So what's in that quotient is exactly the average velocity. This is the average velocity over the interval 1 comma t, okay? So what we're doing in the limit is taking the limit as t approaches 1, and we get the derivative there, okay? So let's go ahead and calculate the derivative here and see what happens. So we'll use our derivative formulas. So s prime of t is negative 32t plus 0, okay? Remember the original function was negative 16t squared plus 100, okay? So the derivative is this, and therefore s prime of 1 is negative 32, okay? And that's exactly the number that we seem to be approaching here as we take smaller and smaller intervals of times starting at t equals 1, okay? All right, so the conclusion of this, guys, is, and the point of this is something you already know, which is that the derivative of a position function measures distance traveled, okay, or distance from a fixed location. is the velocity function. Okay, so it gives the instantaneous velocity, which is redundant. If I just say velocity, we're talking about instantaneous velocity at time t. So here's position at time t. This is velocity at time t. Okay, and if you continue this, so sometimes we call this v of t. If you continue this, if you take the second derivative, remembering that's just the derivative of the derivative, you get the instantaneous change of velocity, which we call acceleration at time t. Okay, and sometimes this is represented by a of t. All right. Okay. I don't want to do anything else with this at this point, but next week when we come back together, we will talk about integration as the inverse of differentiation, as you guys know. And so what we'll see is sort of the following pattern, is that if we start with position and differentiate, D is I'll use a capital D maybe, okay, for differentiate, that brings us down to velocity. And then if we differentiate that again, that brings us down to acceleration. The antiderivative, okay, or the indefinite integral, as we sometimes view it, okay, will bring us back up. So if I take the antiderivative of acceleration, I get velocity. And if I take the antiderivative of velocity, I get back up to position. Okay. All right, guys. So this is sort of the theme I want to get going. And then next week we'll come back together, talk about integration. Okay, define integration, and just review the definition, look at some differentiation, or excuse me, anti-differentiation rules, and some quick applications, and then move on. All right, hope you guys have a great day. Be safe, have a good weekend, and we'll see you on Tuesday. Thank you very much.